Good evening, my name is Alexandra Suvorikova. Today we are going to present our joint work with Professor Spokojny and my colleague Nasar. We will talk about multiscale change point detection. The talk will be divided into two parts. The first part concerns the algorithm description, and the second part is complete mystery for me, as it was prepared by Nasar, but I hope it will be interesting. Okay. The problem of change point detection is quite popular nowadays. It arises in different realms of data analysis like econometrics, bioinformatics, quality control, or even network security. The main goal in this problem is to find out a time moment when the stochastic properties of observed data flow changes. For example, on the picture you can see actually two examples of change point. The first example is change jump in mean, and the second change point is a change in variance. So structural change is a relative concept. Naturally, the problem can be stated as follows. Let Y be the set of observed data. We will say that there exists a change point N, so if all data before this time moment N were distributed according some unknown, maybe unknown, random law P, and after that moment it is governed by some other stochastic law Q. P or Q could be unknown. This problem can be easily reduced to the problem of hypothesis testing as soon as we have a candidate for a change point. Let's assume that N is our candidate. Then our baseline hypothesis is that there is no change point and the data is homogeneous. And its alternative is that N is change point and then the data is heterogeneous. In this work, we mainly focus on online change point detection. It means that we would like to find out a change point as fast as possible, and we would like to find out some trade-off between the false alarm rate and the delay of the detection. Well, as the topic is quite popular, there are a lot of standard methods that solve this problem. They can be, for example, classified as parametric and non-parametric approaches. In parametric models, we make preliminary assumptions about the nature of observed data, and in non-parametric approaches, we have no such assumptions. Both of these methods has its drawbacks. For example, if we made a wrong parametric assumption, the algorithm is just crashed and nothing works. And if we use non-parametric approaches, they are usually less sensitive and need larger sample size that makes them not very acceptable for online change point detection. In our work, we solve three problems. First, we use parametric assumptions, but we say that the model can be slightly misspecified. Second, we will try to find the compromise between the false alarm rate and delay of the detection. And the most important part is to allow algorithm to be tuned automatically by the data. We call it multiscale change point detection. The description, brief description is on the slide. First, we are looking for structural changes using likelihood ratio test statistics in a running window. Then we are looking for a change point pattern. I will talk later about them. And the last point is we tune critical level for test statistics using multiplier bootstrap procedure that was already described by Maya today. First, we use likelihood ratio test because it has very nice statistical property. Under some assumption on the smoothness of parametric family, we can show that likelihood ratio test statistics behaves, even if the model is misspecified, it behaves like chi-squared random value. Moreover, it behaves like ordinary chi-squared with p degrees of freedom, where P is the dimension of our parametric space, if there is no change point. But if there is a change point in the sliding window, there appears a systematic drift, and the likelihood ratio test behaves like non-central chi-squared distribution with a drift that is proportional to the L1 norm of change point. So the idea of the proof based on non-asymptotic Wilks and Fisher theorem. Today I will omit these details, but if someone wants to discuss it, I will be glad to discuss it after the session. Then we found out a very nice thing, that likelihood ratio test change its behavior in the neighborhood of a change point. It means, for example, on this picture you see a change point, a step change point. In its neighborhood, likelihood ratio test behaves like a triangle. If you have a look at this data, there is a break in trend. Likelihood ratio test will on average behave itself like inverted triangle. And the third example is smooth transition between two parameters. In that case, likelihood ratio test statistics behaves like trapezium. This is very important thing. It will allow method to be more robust for outliers. We can easily prove that using the property of mathematical expectation of normal distribution L1 norm, and that it can be approximate our expectation of our test statistic.
Because here in this approximation, the left-hand side depends on T, and the right-hand side
should also depend on T.
So this is
yes, C for each T, yes.
And what you plot is dependent on T. So
on T, yes, sorry.
So this function of T, and this d theta is exactly the pattern.
Yep. Yep.
D theta is actually triangle function.
Yep. So instead of observing likelihood ratio test, we use its convolution with desirable pattern. It provides robustness of the method. And then we use multiplier bootstrap for tune critical values for test statistics. There should be t hat also, sorry. And the last part is multiscale approach. It means we would like to find out the trade-off between the delay of detection and false alarm rate. So we are looking for this pattern on different scales simultaneously. So the higher the number of scales where can we find that this pattern is overcome our critical line, the higher probability that there is a change point. So that's more or less the yes, there are. Top line is observed data, it's Gaussian data, and the rest is likelihood ratio test convolution with the pattern calculated in different different sliding windows of different sizes.
Is it shifted in time because your test statistics
No. It's shifted. Yes, it's shifted. It's aligned. Here you can see the pattern. It's 4 points, 10 points, and if you use the window of the length 20 points, you can see almost the triangle.
So if you take larger window,
yes.
Then test statistics become significant.
Yes, I will show you. For example, here, unfortunately, the picture is very small, but you can see also 3 different scales, and the red line is a bootstrap threshold. Yep, the last picture you can see that there is an obvious, almost triangle pattern.
About significant part, big window requires your delay.
Yep. So if you want to detect change point fast, you should use smaller windows. If you want to be more sure that there is a change point, you should wait for the results on bigger window. Yep, that's it. And the next part is for my colleague. Please, Nazar.
Alexandra, thank you for the first part. I will continue with two misspecification examples. I found it could be you could be curious in these examples because usually when we deal with some data, we restrict our mind by some parametric model, and sometimes it is interesting to know what is outside that model. So turning to change point, as was already said, we couldn't find the real distribution. We only take the closed parametric approximation for this distribution, and we know if the projection into parametric family is changed, then we will detect a change point. But what if the projection didn't change, but at the same time we will change an orthogonal part of the distribution? Will we found the change point if we live only here in this parametric family? So it is a question, and maybe it is not clear, but if somebody wants to answer, I will wait for a moment.
Use another parametric family.
No, I mean, if I use this parametric family and the projection didn't change, at the same time the orthogonal projection changed, what it will influence on? Will it increase? I could turn to the statistic, which is likelihood ratio, and we have proven that it is non-centered chi-square distribution. So if we didn't change theta, this component will be 0. I mean, component designated by delta d theta. And under this condition, if d theta is 0, will we detect a change point? Probably not, but in some cases we can detect. As an example, suppose. Consider the model when our parametric model is normal with fixed variance, and mean is our parameter. The real distribution is changed from variance equal to 0 to variance equal to 5. And here in this plot, I displayed the data by the green points. Blue is our statistics by which we detect the change points, and an orange line is a critical value. I mean critical value for xi plus the theta parameter, which is defined by bootstrap simulation. So as you can see, when we increase the variance, the statistics could easily overcome the critical value, and even if model only looking for changes in mean, it will found also changes in variance. Even if here there are not change point, but if we remain the same upper bound, it will found multiple change point. So it was our first problem, because of which experiments become not very good. Maybe I will take a message from my message from that example, but that in the theory we usually treat a variable xi that is used in our statistics. We treat it as a standard normal, but when we take the data from unknown distribution, we should change our mind and didn't consider xi as a standard normal variable. Another example. We live in our parametric family as in previous example, but this time we didn't change an orthogonal direction. We only make changes in parameter. But when we take, for example, this window, which is rather large, the mean parameter became at the same level as previously, where we didn't change the parameter. So no, as you can see from this picture, it's I think it's rather clear. And I have the same question: will we find the change point here? No? Okay, let's look at the similar plot. Here I keep the distribution which is normal with fixed mean and variables, and this distribution is a mix of two normal distribution, but mixed mean and variable is constant. So as you can see, we didn't find a change point according to the blue statistics, but at the same time, our border, which is defined by bootstrap simulations, become extra high. So why it become extra high if we should consider the top value of this blue line? The explanation also could be done with a rather simple example. We consider two likelihood functions, one with weights which allows us to make bootstrap simulations. And here, xi variable that is used in our statistics is has additional component, which is 0 when all our weights equal to 1. So without the weights, we didn't notice this fluctuation in parameter. So it corresponds to the picture when we change parameter theta, which is mean, around the mean value. And it produces additional sum here. And because of it, the variance of the bootstrap xi becomes larger than this variable in the real world. Okay, and I will come to experimental results. As usual, we will use normalized mutual information to measure the distance between partition of the timeline returned by the change point algorithm and the reference partition of the timeline by reference change points. Here are the results. We've used data from Poisson distribution, and our family is normal. Here we compared our algorithm, which is blue, to standard change point detector from R package and Bayesian online change point detector, which currently works better than the discussed algorithm, but we suppose it could be improved by changing the model, which account not only changes in mean, but also changes in variance. Here there are links to the software for the algorithm used in this presentation. You can download our method from the GitHub and also look at the demo, which is the first two links. And also there are link for the Bayesian methods and methods from R package. So I will finish by this. To conclude, I will remind the main points that we propose the algorithm that didn't sensitive to my specification, and this is done by finite sample theory, which is used in many applications, and also we applied Bootstrap. So thank you for your attention. Any questions?
We have time for several questions. Well, I have a question. So you propose a new method for change point detection, and in case when there is no such a big model specification, like very ordinary, does it work better than other methods, or did you compare?
So I compare it work even done better if we have a specification, but usually without a specification we only can suppose that our methods improve the quality because of multiscale. This allows us to find quickly rather high changes in value in distributions. And at the same time, if we also want to find small changes, we can use bigger windows, which allows us to cover these two cases when other algorithms didn't use this approach, as I know. So the idea is that we can reinforce methods by using using different levels of statistical significance, which is designed for different strengths of the change point.
Nazar, okay, as far as I understood, so there are no other software packages which use multiscale, but do you know some other methods? I mean, in some other papers they probably also suggest multiscale for some other procedure, but
I haven't found other multiscale methods, but I think they exist. Can find it.
I made a review of literature which not so there are not so many such methods. Moreover, there are not so many methods which work with high dimensional data, and our method can be easily applied for high dimensional parameters.
have you tried?
Yes. Nice, I like it.
Okay.
Unfortunately, we didn't find a good method to compare with.
Yes.
Because all others fail.
No,
Yeah, no, because they are all for one dimension.
Okay.
Standard packages usually for DNA analysis and so on and so on. They are usually for one.
Oh, wow. Okay, thank you.
Thank you.